Thank you very much. I thank organizers very much. Yes, so that's true. I'm coming from group theory, so yeah, it's a problem a bit. I mean, there are graph theorists here and group theorists, and I tried to prepare talk to please everybody. So it probably means that I will please nobody, but let's try. Okay, so the choice is weakly modular graphs. I will speak about them. I will explain what's that. So let me say first, for this graph theorist part, that what we do is that we want to conclude some properties of groups, like you know groups, just looking at their actions on some spaces, in particular on some graphs. So I personally like graphs because they are combinatorial objects, and you will see. I hope to mention why it is good. And so basically, then I mean, if you know this strategy, then basically you work then on the spaces, with the spaces, and from some of its properties you automatically can deduce some properties of a group. So I mean, groups are behind, but usually we will study spaces or graphs. Okay, so most of the talk will be based on the paper with Victor and Jeremy and Hiroshi. And yeah, and actually main point of this talk is to ask you a question. It will be at the end, nearly. Okay, so what's weakly modular graph and why weaker? So here's the definition of the first condition. This is called triangle condition. So I will not read this. I will say it in my words. So I mean, this is a picture to this condition. So it says also this condition TC UK, U is just a vertex, K is a distance from this vertex. Actually, those are pictures from this paper. I copied them, so I hope I could. Jeremy did them. So if you have two vertices joined by an edge, so adjacent vertices equidistant, a distance K from you, both of them, then you know there exists a vertex which is adjacent to both of them and which is closer to you. This is the condition. This is this TCUK condition, triangle condition with respect to vertex U at distance K. There can be many of such vertices, but there is one. Okay? Yeah, of course, feel free to interrupt anytime. Okay, so this is the first condition that we are interested in. Here is the second one, quadrangle condition. Yeah, I hope you can guess where the name comes from. So it is similar, but now you have quadrangle. So now the setting is like this. You have three vertices. Again, V and W are equidistant at distance K from you. But now they are at distance 2. They are not connected by an edge. And then there is a vertex Z, which is one step farther from you. So Z is a distance K plus 1 from you. And then you claim, I mean, you want that there exists a vertex nearly the same as before. I mean, again, closer to you, a distance K minus 1 from you, and adjacent to V and W. Yeah, probably I should also explain some words here. So for me, graph means simplicial graph. I mean, this is, we are kind of geometers, so we really work with simplicial things. Simplicial means that this is undirected graphs without loops, I mean edges that are loops, and double edges, multiple edges. So simplicial. And yeah, okay, so that's quadrangle condition. And again, there can be many of x's, but there exists one. Okay? So that's it. Namely, now you say that a graph is weakly modular if it satisfies such conditions for all U, for all vertices, and or all K at all distances. Okay? So this is a global condition. I mean, you have to check your whole graph. One more disclaimer. Yeah, this is the subject of continuous conflicts between me and Victor and Jeremy and others. That usually I think about infinite graphs. So graphs are usually infinite. Well, I know you don't like. I mean, you can think about finite part of them. It's what we do actually mostly at the time. But there are, for me, interesting graphs are infinite because this group theory that we are doing is about infinite groups. Okay. Okay. So this is weakly modular graph, and this is, I believe it's an important class of graphs because it unifies a lot of graphs that you saw already today during the first talk. And so I will say more on this. And yeah, and this class of graphs was invented by Victor. So long time ago, you see it's ancient, it's some cuneiform or runic alphabet. So here you can see Victor's name in Cyrillic. And also you see it's ancient because it's some ancient version of LaTeX. So you know, and it's him who did it. Okay. It's correct, right? Yeah. What? I know. Okay, I stop making jokes. Okay, so here is what it generalizes. So most of this you saw during the first during the Fedor talk. So for example, and here is double terminology because there is this division in the audience, right? So median graphs for graph theorists is a one skeleton of K0 cube complexes for group theories. Okay, so these are weakly modular. Bridge graphs, and for the right people, one skeleton of systolic complexes, also weakly modular. Then weakly bridge graphs, one skeleton of weakly systolic complexes. This is actually, this is the class that we introduced with Victor during our first encounter. Yeah, so, yeah. And then modular graphs, you should know it, I mean, at least you should maybe meet the name from modular lattices. In lattice theory, it's an important class. And then bucolic graphs, then we also with Jeremy and Bostian and Tanya introduced such class, and quasi-median graphs and Helly graphs that are of big interest for me now, and we speak more about them. So all of them are weakly modular. And there is more. There are more classes of graphs, but yeah. And still, it is very general definition, and still you can get nice properties out of this definition, and I will speak about some of them, just some of them. Okay. So here I want to say a word about geometry group theory. So as I said, it's studying groups by looking at actions of those groups on spaces, on some spaces with some geometry. In this particular case, it will be by studying actions of groups on graphs and on associated complexes. I will say a word about this. So I see this part of applications, applications of graphs in this context in two ways. First of all, we can use these graphs and their properties, the properties that will be referred to later in more details, the properties that some of these classes of graphs can be detected locally, whatever it means. You will see in a moment what it means. So you can use it to construct examples of groups, new groups. And this was, for example, the case for introducing the bridge graphs to geometry group theory. On the other hand, you can also study classical groups. I mean, the groups that we already know. I mean, they are somewhere. They are given by some other, I don't know, theories or from some other sources, and then maybe equipping them in some structure of group acting on some nice class of graphs. Graphs can help us to understand further properties of these groups. So both of those happen, and yeah, I will show you some examples. But I see such an alternative in applying graphs to groups, at least the classes that I'm studying. So here are examples. This is very egocentric list, of course. So here is what kind of groups we were able to construct really using the tools from graph theory. So, highly dimensional Gromov hyperbolic groups. I mean, they existed such, but they didn't exist in some cases, for example, for Coxeter groups. So then those guys from Wrocław, Januszkiewicz, Tadek Januszkiewicz and Jacek Świątkowski, they constructed such groups using bridge graphs. Actually, they reinvented them and they called them systolic complexes, I mean the associated complexes. And also, yeah, either bridge graphs or median graphs. I mean, there are constructions using both. So yeah, I should say probably that this was, I mean, on base of this was the reason of my first visit to Victor. And this was, yeah, there is a story that's a bit embarrassing for me, but well, I will tell it. Because Januszkiewicz and Świątkowski called their complexes systolic complexes, and then, you know, they are using some complexes, simplicial complexes, and links, and I don't know, some simplicial terminology. And then we found out that there are guys in Marseille and in other places also doing bridge graphs, and that seemed very, very similar, nearly the same modular that we couldn't understand a word from the papers because the language was totally different. And those guys, like Victor, they are in computer science department. Like it seems that in France, graph theory is computer science. So this was very exciting for us because we thought, oh, so we are great mathematicians and there are computer science guys, and we'll just ask them where we can apply in computers our great theory. So I came to Marseille for like a few days, for 4 days or 5. And the first day I asked Victor, okay, so just tell me what are the applications? I know everything about these bridge graphs. I just need applications. Maybe I thought about money. I don't know. and he looked like disgusted at me, and he said, "I'm not a computer scientist. I don't know anything. I'm just mathematician." So I was totally depressed. I mean, the first day I came in and I was totally depressed. I thought, oh my God, why I came here? I mean, but then then I learned that they know much more about systolic complexes that we did. And yeah, and since then, and the next days actually were quite fruitful with this weekly modular, with this weekly systolic graphs and other things. And they, yeah, and I mean, they helped us to prove many theorems. I mean, help means that they proved it, but we just asked questions, right? Questions. Okay, it's not that embarrassing, but a bit. And actually, this construction, just to go a bit off, this construction has even further applications, it appears. So just to name two, so the construction of this Gromov hyperbolic groups, high dimension, whatever dimension means, has actually applications, for example, in commutative algebra. So there are two teams, just to mention, that there are really real-life applications. Maybe not in computer science, but those are applications. Yeah, you don't agree, Victor, probably? They are not maybe so profitable, but they are good. Okay. Yeah. So here is another. This is about. Yeah. This is not that connected, but it is about. We can construct some interesting groups, some very exotic groups, using, for example, small cancellation. And small cancellation is not on the nose weakly modular, but it is the same kind of idea. This is the same kind of idea that we call combinatorial non-positive curvature, whatever it means. And actually, as you saw, the title of the paper with Victor, it's weakly modular graphs and non-positively. What's the title? Oh, yeah. Non-positive curvature aspects of weakly modular graphs, or something like this. And so this is this. So non-positive curvature, as some of you, as geometers, know from manifolds, from Riemannian manifold. is some idea that actually is behind, I mean, that is the idea through which I see weakly modular graphs. So we will see example of such behavior of non-positive curvature behavior in a moment. So I just mentioned them, and for example, median graphs are also used by me to some construction of some Burnside groups. Anyway, and so this all is related to weakly modular graphs. So this is the first type of applications in group theory, and here is the second. They are used to studying existing groups. So what I see here is there, right? Okay, so I can see. Okay, so for example, median graphs are, or cat-zero cubical complexes there was a, I mean, there is still a big effort, but this was a big breakthrough by Agol and Weiss in studying free manifold groups. So here I just list some names of participants of this conference. So Piotrek and Jingin were working on this, for example. The other ones are arting groups. It is a mysterious class of groups. That is, Gridged graphs. Yeah, Gridged graphs are, it is very mysterious class of graphs related to bridged graphs. Just for the sake of this talk, think about them as about bridged graphs. So they are studied to, okay, they are useful in studying arting groups. So arting groups is an old class of groups, but very mysterious. And we were able with Jingin to prove something new still about arting groups using exactly Gridged graphs and median graphs. And you will see, so I'm advertising Jingin's talk. It will be a bit about this. So there are some graph products, also our collaborator, Anthony Genevois and Motius Valunas, attendant, participant of this conference. They were also working on them using quasi-median graphs, which are very related to bucolic graphs that you saw. And other instances are, for example, some Coxeter groups. I mean, Coxeter groups are very well known. However, their combinatorial structure in this sense, I mean, to show that they act on some combinatorially non-positively curved spaces, like some weakly modular graphs is not known. And for example, Zachary Munro was able to show that some Coxeter groups act on weakly modular graphs nicely. So it's as far as he can go. I mean, really, in this generality, I mean, weakly modular, not any specific, more specific class. And, it's, and Heli groups. So Heli groups are groups acting nicely at Heli graphs, and this is actually, this should be the topic of my talk, but, well, I chose otherwise. So this is, for me, the most intriguing project now, and nowadays it's also the subject of our recent paper with Jeremy and Victor and Hiroshi and Anthony Genevois. And I believe there is a big potential, and there is a lot of groups acting nicely of Heli graphs. So like all Gromov hyperbolic groups, cat-zero cubical groups, and many, many other groups. And there is nowadays a community of people working on this, I think quite intensively. So even among participants of this conference, so you just pick a name, you just pick a letter, and you will find many people like with names starting on this letter, like H, and you have Hirai, Huang, Hoda, Heter. So with every letter you can do the same probably. So it's really important topic. Okay, so this is why we like them, why we like graphs, and why we like in particular weakly modular graphs. All of them, I mean, all the classes here are weakly modular graphs. So they seem to be important even for us. Okay, and here is a bit why they are useful and why and what we know about them and how we use them. Namely, there is a local to global characterization. Actually proved one of the main topic of our paper, the main source listed at the beginning. So for this, to introduce them, I have to define a few things. So a graph is locally weakly modular if it satisfies the same condition, so triangle condition and quadrangle condition, but I mean for every vertex, but at a limited scale. So you only check it at scale 2. So it is local condition because you only need to check the balls of radius, let's say 3 in this case, but of finite, I mean of definite radius. So you just check in every point, you check a ball of radius free, and you look whether these two conditions, I mean TC_U2 and QC_U2 work, and then that's it. Note that the weak modularity condition, so triangle condition, then this general one, and quadrangle conditions were the global conditions. You have to check very, very big distances, very, very big balls, and I mean, looking at the graph only in the limited, in locally, even everywhere, doesn't tell you anything. So, but locally weakly modular is different. This is really a local condition. You just check locally. So, yeah. So this is, I mean, it is some analog of Gromov's condition for cat-zero cubical complexes. So just something checked locally, or local K largeness or 6 largeness for bridge graphs or for systolic complexes. Okay. So here's what we could prove. So we could prove the local to global characterization. So let me explain it for a moment. What is it and why is it important? So it says that the graph is weakly modular. So remember, this is a global condition, if and only if it satisfies this local condition, and moreover, its triangle square complex is simply connected. So what's triangle square complex? So this is a polyhedral complex whose one skeleton is your graph, and where you add cells that are triangles and squares, so thrigons and fourgons, whenever you see their boundaries there. So whenever you see in a graph triangle, I mean three edges, cycle of 3 edges, and quadrangle, meaning cycle of 4 edges. So then you glue in respectively triangle and square, okay? And if you do it, you've got a polyhedral complex. So you've got some non-trivial topology, right? I mean, yeah, graphs have maybe not trivial topology, but I mean, you know, there are not much dimensional phenomena there. So here you can get some higher homotopy groups and blah, blah, blah. So you've got some topology to do, but when your graph is weakly modular, this triangle square complex has to be simply connected. Simply connected means that every loop is contractible. So whenever you have a loop, for example, and in this combinatorial category, you can think about path in one skeleton. This can be contracted to a point, okay? So for example, cycle of length 3, just 3 edges is not simply connected, but if you add the triangle, then it's simply connected because this loop can be contracted. So, okay, so this is what we prove. I will say just a word on the proof, not really give you a proof or even idea or even slight taste, whatever, but I will say something. Let me just say why it is important, why we are looking for this. And actually, most of, well, maybe the whole career of coming to Marseille for me was proving such kind of theorems for various classes of graphs. So why they are important? Well, they are important for our group theoretic purposes because we really want, I mean, so if we often have some objects that are defined locally. For example, the so-called presentation complex. So if you have a group, you have a presentation of a group, then immediately you have some presentation complex. If this presentation is finite, then you've got finite presentation complex, and this is object that it's not simply connected because exactly its fundamental group is the group whose presentation is this presentation. So then universal cover of this complex, of this presentation complex, is simply connected. So if you check, so basically you can check some local things with this finite presentation complex, and then universal complex by definition is simply connected. So you will know that the complex itself maybe has no good properties, but its universal cover has good properties. And it happens that a group acts nicely, whatever nicely means, on the universal cover of its presentation complex. So this is it. I mean, if you can any class of graphs, if you can detect it by some local conditions, modulo this simple connectedness, then then it's good for us. I mean, then from the point of view of groups acting on such complexes, you are in a good position. So we are often interested in such properties, and moreover, this is I mean such kind of theorems is referred to often as kind of Cartan-Adama theorem, because I mean like the first instance or the standard instance comes from manifolds of non-positive curvature. When you say that if you have a manifold that is also, for example, in the case of cat zero, whatever it means, spaces, if you have something locally cat zero and simple connected, then you claim it's cat zero, and cat zero is an important non-positive curvature notion. So this is meant to like mimic this kind of non-positive curvature. And non-positive curvature in this sense is important. I mean, it gives you a lot of nice properties for groups acting on such spaces. So, by the way, in the same paper, so this is the paper that I mentioned at the beginning. In the same paper, we also proved it's kind of corollary. I mean, but far going corollary of this theorem. Yeah, you say no. Yeah. It's okay. It's something that looks like far-going corollary of the same theorem, and it's proved similarly. So we proved that the graph is Heli. So let me just remind quickly that we saw it already. I mean the Heli graphs. So graph is Heli if the family of balls in this graph satisfies the Heli property, meaning that any family of balls, of pairwise intersecting balls, has an intersection. So this is a family of any balls. So this is global condition, and here you can again translate it into the local condition. So click Heli means that maximal clicks satisfy the Heli condition. So it means that any family of pairwise intersecting maximal clicks in a graph has an intersection. So this is local because clicks are of diameter 1, right? So if they intersect, you are at most in diameter 2. So again, you have this graph is Heli if it satisfies this local condition, and then its triangle complex is simply connected. So here in Heli graph, you only need to kill triangles. It's not true in weakly modular graphs because like the square, I mean the foregone is weakly modular, and of course there are no triangles, so there is nothing to kill, but still homotopy is non-trivial. Okay, so yeah, so this is a related result, and this is actually the base of this, from my point of view, burst of using Heli graphs in group theory recently. So yeah, we are very proud of it. Okay, so let me say a word on the proof. Just a remark. So one direction that weakly modular graphs satisfy this local condition and simple connectedness of the triangle square complex is quite easy. So first of all, if you have a weakly modular graph, then it's obviously locally weakly modular, right? You just look at some distances, not at all. And second, here, I mean, these conditions, the triangle condition and quadrangle condition, actually tells you that all the loops are contractible, and so actually those arrows, those implications are the contractions of a loop, right? So if you have, assume you have a loop here, and part of the loop is this edge, then you simply can, if you add triangles, then you can like deform this edge to those two edges, and some notion of complexity, some complexity decreases. I mean, like, okay, I will not go into details, but you see, this guy is closer to some vertex than this guy. So then you go farther, and similarly you do with vertices that are I mean, with edges that are not equidistant. So this part of your loop, maybe this is a loop, there is a loop here, and this is a part of it, and if those edges are not equidistant, then you can contract it, you can deform this part of the loop through this square that you added. And yeah, and respectively, using those two moves, you can contract any loop, right? Towards, for example, U. Okay? So here is why weakly modular graphs satisfy those two conditions, the local condition and the global but topological condition on simple connectedness of the associated triangle square complex. The other direction is difficult. Well, actually, it takes many pages, and I could give some idea, but I decided not to. It takes some time. So just to give some slogans, the other direction is done by building consecutively your graph, building by balls. So you build the balls of your graph, one radius after another, and you check that the way you build the balls actually is determined only locally. I mean, if you have some process that if you keep this process working on locally in some small balls using these local conditions, then actually you will get what you wanted. You will get your graph. So this is, well, actually for those who know the proof of the fact that every space with some, crazy, nice conditions. I mean, the conditions that are not for crazy topologists. If you have a nice space, then universal cover of this space exists. This is by simply taking the space of all paths. So it's exactly the same proof, but in combinatorial terms. We take the space of all paths, and we have to identify some paths, but actually it happens that identification goes only locally. And this is also an instance of non-positive curvature, because if you have positive curvature, then usually what happens is that such paths should be also identified when they are far from each other. In non-positive curvature, it doesn't happen. So it's just a slogan. Sorry for this. Okay, so that's the proof. But there is a bit more about this. Namely, in fact, in many cases, like for median graphs, so K0 cubical complexes, or for systolic complexes, so bridge graphs, or for heli graphs, you have more than simple connectedness. You have contractibility. And of course, just killing the two cells, some two cells, like I did here for triangle square complexes, I just added two cells, meaning of dimension 2, cells of dimension 2, some triangles and some squares, cannot kill some higher homotopy groups. So for example, if you have simplex, then if you add only triangles, then this simplex will, like free simplex, if you have a free simplex, you add only triangles, then this simplex will become a topologically, it will become a two-sphere. So it is simply connected, but it has higher homotopy. So adding just two faces cannot kill this other homotopy. So in particular, for weakly modular graph, if you do this triangle square complex, then this triangle square complex is not necessarily, and usually is not, contractible. So in some cases, in many cases of the graphs that you saw, some subclasses of weakly modular graphs, like I mentioned, median graphs, heli graphs, bridge graphs, you know what cells you need to add to make the complex contractible. So this will be a question in a moment. So just note that we can get better than simply connected in many cases. You can get contractible, and the proof is basically the same. I mean, because some other conditions, yeah, but by the way, the other classes like median graphs and bridge graphs and other graphs, heli graphs, are defined by similar some better versions of triangle and square conditions. Okay, so this is the first, yeah, and this contractibility also fits this point of view of non-positive curvature, because usually from non-positive curvature we expect that the space is contractible. So all these classes for which, okay, that we had actually satisfied, they have this contractible complex. You have to add more, but you get contractible complex. So you really have some nice non-positive curvature condition. On the other hand, this proof of simple connectedness that I showed you, and actually the triangle and square conditions also tell you something more, that not only, for example, you know how to contract loops, but you can contract them in very controlled manner. So for example, So for example, if you have a big loop, then you can see that I mean the loop is of some length, let's say L. Then you can pick a vertex that such that the whole loop is a distance at most L from this vertex. So it means by these two conditions, but by these two moves applied consecutively, that you can contract this loop in about L square moves. And this is the so-called quadratic isoperimetric inequality, that holds for weakly modular graphs or for triangle complexes. So this property, this gives you not only simple connectedness or in many cases even contractibility, but it also gives you better control. For example, giving you quadratic isoperimetric inequality that for group theorists, for example, translates to solvable word problem for a groups acting nicely on such complexes. So there is more behind these conditions than just simple connectedness. And this is the main point of my talk. I have a question to you. But because actually we have no good complex for weakly modular graphs. So what means reasonable? Well, there is many words to say. So first of all, as I said, we want it to be contractible. But you do not want to do some stupid constructions like span a click on the whole complex, because then it distorts a lot distances. Because usually, as I said, my graph is infinite, so usually it means it has infinite diameter, and then if you span a click, it becomes diameter 1. So you want it to be contractible. You want it to be, okay, let me just use forbidden words, quasi-isometric to the graph. You want that group action on a complex extend or induces an action by automorphism on such complex, and so on. So all the complexes that I told you, like median and bridged and bucolic, are, I mean, the complexes, corresponding complexes are of this type. So for example, in median graphs, you fill cubes. Whenever in a median graph you see one skeleton of a cube, you add a cube there of appropriate dimension. And after filling all such cubes, your complex will become contractible. For weakly bridged and heli graphs, you fill simplices. So you just, whenever you see a click, you glue in appropriate simplex. For bucolic graphs, we fill in the prism. So yeah, so the sad fact is that we do not know what to fill in weakly modular graph. So one more condition on being reasonable would be, we believe, that if you have locally finite weakly modular graph, then it's enough to fill finite, some finite dimensional cells, and the dimension of these cells is bounded by this degree of the graph, for example. So as I said, such a complex would not only give us this nice property saying that a weakly modular graph is contractible, meaning that if you have locally weakly modular graph and you take its universal cover is contractible, which is exact analog of Cartan-Adamar, but it would also give you, we believe, I mean, if it's defined properly. So this is in this definition of reasonable. It would also give you this nice control. It would give you the so for example, it would give you, we believe, bioautomaticity of groups acting nicely on such graphs, which happens in all these cases. So just using these triangle square conditions or their analogs, we can prove that groups acting nicely on such graphs are bioautomatic, and bioautomaticity is an important property from geometric point of view. So yeah, just let me say a word. So I said, so this triangle condition basically and quadrangle condition basically tells you that tells you how you can approach the vertex. If you are far away, what path you should choose to go here. So this is the base of proving, for example, bioautomaticity or other nice conditions for other classes of graphs that we have. So even if this X is not unique, then in many cases you know that this X, that the set of such X's is controlled in a way. And then you can say that going from this edge towards the point, towards the vertex, is via the set that you control, and then you go farther again by similar condition, and so you have some kind of normal paths. And normal paths is where you start when you look for biautomaticity. So what you should expect from this complex is that from such a, for example, from such a vertex there is some cell hanging on that you can detect using repeatedly this triangle and square condition. And but detecting what kind of cell is it is quite difficult. Okay. So basically, it will be nearly the end of my talk. Let me just say, so this is a question. Maybe someone knows. So for more precise question, actually, you have a candidate for such complex. So in our paper, we even list some candidate, and we check that this works that this candidate works and gives you the complexes that you saw. For the subclasses that you saw. So if you want more details, please look there. And this is for us most important question on weakly modular graphs. Yeah. So just remember this condition and come with some good ideas. If you want to remember these conditions, they are maybe not that easy to remember. You should make a plate, right? So to stare at them all the time. So like such a plate that you can see the condition, right? And if you want someone to remember these conditions, you should just make such plate and give it to a person, right? So this is a plate, and there are persons who need to know what are weakly modular graphs, right? So so it is. Okay. Yeah, please. Yeah. You can. Okay.
Thank you, Damian.
Learn, study.
So do you want to add a comment?
Yeah, thank you very much. And
what you say, because I have more embarrassing stories. Yeah.
No, but I would like to say that with our collaboration with people from geometric group theory, and all the time I was wondering why they understand me. But Damian make all efforts to understand me and understand me easily. Me not, it's not symmetric relation. And I had the same with Mark Hagen. But I think that Damian make all efforts, and his talk was for graph theorists, was not for group theorists, I think.
Oh, okay.
And was very pedagogical, thank you. And I think one precision that for this systolic bridged stuff, I think that I found the paper by Januszkiewicz-Świadkowski, searching by a paper by Świadkowski, and then I wrote them, and they somehow you come to Marseille, and the main conflict between us is not about infinite and finite graph. This was a bad habitude coming from Fedor. About finite things only interesting, but essentially the conflict is about using the notation gamma and G for graphs and gamma for groups, or vice versa. I think that this is the
G for
conflict.
Groups. Come on.
For us, G is graphs and gamma is groups. Yeah.
G is for groups. Oh.
Yeah. Thank you very much.
Yeah, but this is true. This is true what Victor said. I mean, once I was in Marseille, and there was Nicolas Touican that group theorists know, and I was giving talk, about our stuff with Victor, and then I learned, and Nicolas said it exactly, and talking to Victor, the parts that group theorist like Nicolas understood was not understood by graph theorists, and vice versa. It was really a strict distinction. So yeah.
Two questions. One very quick. On page 12, when you click Helle, can you substitute there one Helle For example, for neighborhood, one neighborhood.
Yes, yes, yes. Actually, it was our first.
Yeah, from application perspective, I would say, or algorithmic, this is better. One neighborhood than clicks are harder to find. One neighborhood.
Yes, yes. Actually, I was surprised that the question.
Yeah. The second question about to avoid completely this, to be clear graph theory talk. So, can we substitute complexes with this condition on connectedness of simply connectedness of complexes just with graph theoretic dismantling schemes that
yes.
You thought it's much stronger? No. Yeah, dismantling scheme means that if, for example, cubical complex there, yes? So you consider cube and you can eliminate any portion of that cube and again any portion of cube until you kind of reduce to nothing.
Yes, yes. Yeah,
so
it's exactly the same. My elementary mathematical culture tells me, I mean, I was taught about topologies and things like this. So this is just another language, but this is exactly this. I mean, you can translate it into totally combinatorial terms. Yes.
Okay.
It's just to make it quick, to formulate it quickly.
Is there any other question for Damian? No.
Just a quick question. These laws from the modularity and the square rule and the triangle rule, they look so much like for directed graphs actually, or pole sets. Like if you draw them like that. So I was wondering if there's a useful or directed graph or pole set analog of these classes.
Yeah, I do not know. So probably Victor knows.
Okay, so thank you again, Damian.
Thank you.